Okay, so this set of lectures is going to focus on correlation and regression, and these are analytic approaches that are used to look at associations among variables, right? So ANOVA, t-test look at differences between variables, correlation and regression look at associations among and between variables. And so this is the approach that we're mostly going to be using in our correlational or non-experimental studies, although we may be using t-test and ANOVA in those studies as well. And we'll talk about instances in which you would use one or the other at a different point in time. So um, what is a correlation? Well, a correlation is essentially a measure of association, not surprising. And correlation is expressed, so the association between two variables is expressed as a coefficient, and that is often referred to either as a correlation coefficient. Another thing you might hear it referred to as Pearson R. And in fact, when we run our analyses on SPSS, that's actually how it's going to be referred to, as an R or a Pearson R. The sample statistic is represented by the small letter r, whereas the population parameter is represented by the Greek letter rho. And that's most important if you're doing hand calculations. Correlation coefficients range from -1 to +1, all right? And any value that can fall in between -1 and +1. And what they tell us is two things. Correlation coefficients tell us about the strength of the association between two traits or measures. So how strongly related are these two variables or traits? And they also tell us about the direction of the association between the two traits or measures. And I'm going to get into this in a little bit more detail in this next slide, so don't worry if you're not keeping up just yet. Okay, so how does it do it? How do correlation coefficients do this? Well, the strength of the effect, or the strength of the association between two variables, is represented by the magnitude or the size of the correlation coefficient. All right, so remember that those signs, a -1 does not mean a smaller association than a +1. In fact, we're going to see that the sign of the coefficient actually represents the direction of the effect, not the magnitude. So any correlation coefficient that is close to 1 or closer to 1 represents a strong association, right? So values closer to +1 or -1 represent stronger associations, whereas values closer to 0 are representative of weaker associations. In addition to that, if we look over here on the right-hand side to these graphs, right? So we have these graphs and we have this line that's sort of fit to the data here. What we're also going to see is that the stronger the association, the steeper the slope of the line, right? So we're going to see a really steep slope in this case. And weaker associations are going to be represented by flatter slopes, and no association is going to be represented by a flat slope, right? So a correlation coefficient of 0 basically indicates that two variables are completely unrelated to one another. All right, and that kind of makes sense. If you look at this, right, there seems to be sort of a pattern in the data in these two graphs here, and it looks kind of like buckshot in that no correlation, right? It's just all over the place. There's no pattern to the data. So, but how does that pattern, what does that pattern mean, and how do we interpret that? Well, so there's two different signs, there's positive and negative, and they tell us about the direction of the association. So a positive correlation is when the values on two traits change in the same direction. All right. So what we see here is that as the values on one trait increase, we will also see the values on the other trait increase. And you can kind of see that represented here in the graph, right? That on the low end of the x value, we're also getting lower values on y, and at the high end of the x value, we're getting higher values on y as well. An example of this would be the association between outside temperature and level of thirst. So as the outside temperature increases, we're going to see an increase in the level of thirst. Hotter temperatures associated with more thirst, lower temperatures associated with lower thirst. All right, it's not going to be perfect, right? Because sometimes in cold weather it's dry and we get thirsty, but it will be a could be potentially a relatively strong association. All right, so that's a positive association. A negative association occurs when the values of the two traits change in opposite directions. So in this case, we'll see low values on the X variable or the predictor variable are associated with high values on the y-axis. Conversely, high values on the x-axis are associated with low values on the y-axis. And again, you can kind of see that pattern in the data. So an example of this would be outside temperature and the amount of clothing people wear, right? So as the outside temperature increases, the amount of clothing people wear decreases, right? So lower temperatures, more clothing worn, hotter temperatures, less clothing worn. All right, so that would be an example of a negative association, right? So positive association, values change in the same direction. Negative association, values change in opposite directions. All right. In addition to telling us about the strength and the direction of the effect, we can also calculate something called the coefficient of determination, which is represented by this symbol r squared. And essentially r squared is how we calculate it. We basically take the correlation coefficient, we square it, and that gives us the coefficient of determination. This is a measure very similar to eta squared, which I described in the ANOVA lecture. And it essentially tells us the proportion of variation that is common or shared between two traits. So let's have an example. Take a look at this Venn diagram here. Say, for example, that we have a sample of participants and we ask them to report on their overall high school GPA, and then we have them report on their freshman year college GPA. And we calculate a correlation coefficient, and it tells us, R is equal to something. All right, let's say R is equal to 0.5. So we can square that, and an R equal to 0.5 is going to give us an R squared of 0.25, essentially saying that 25% of the variation between these two traits is shared or overlaps. Okay, so this overlap region here is what R square is actually representing. All right, and so what this essentially says is that roughly, again, I kind of gave this example of height, but we can do this, that about 1 in 4 times, if I know your high school GPA, I can accurately predict your college GPA. Having said that, we can also see that there's quite a bit of variation in high school GPA and college GPA that are unrelated to one another, right? So these areas here do not overlap. So why would that be? Well, it's because there's probably other factors that are influencing both high school GPA and college GPA other than one another. For example, in high school, maybe your parents spent a lot of time hovering over your shoulder, making sure you got your homework done, making sure you did it correctly, editing your papers. So that is going to give a boost to your high school GPA. Maybe when you get to college and there's no one looking over your shoulder, you make a bunch of friends, you spend a lot of time out with those friends, you're spending less time studying. That actually puts a little damper on your college GPA that freshman year. So it's these other factors that are going to account for this variation that is not shared, right? And then we do have this small amount, perhaps it represents intelligence or some other things that represent that shared variation. Okay, and that's perfectly normal. We never expect that a single variable is going to be a perfect predictor or a perfect explainer, if you will, of a second variable. Most of the time, behavior is far more complex than that, so we would expect that there would be some other things that could explain that remaining variation, including error of measurement, right? So it may just be that there were mistakes made in terms of people's self-report of their GPA. Maybe people are prone to overestimate their GPA, overreport it because of social desirability, or maybe they just forget. All right, so there's going to be a certain amount of error of measurement that's also going to factor in and influence the amount of overlap we're going to see between these two different variables. Okay, so finally the question is, when is it used? And we're going to only use it for the third reason or the third use, but there are two others. So we can use correlation to assess the reliability of a scale. So I talked about test-retest reliability when I talked to you guys about measures. And essentially what this asks is, does the scale produce the same score for participants each time it's measured? So for example, for an IQ score, an IQ scale to be meaningful, it should produce a reliable score, meaning that each time we give it to the same person, they should get roughly the same score, recognizing again that there's going to be some error in the measurement. So if I give you a score, if I give you a test a year ago and I give it to you again, I can calculate the correlation between those two administrations, and I would expect if the scale is going to be reliable that I'm going to get a high correlation. Usually we consider it to be reliable if it has a correlation of 0.8 or above. We can also use it to assess the validity of a scale. So in this case, I would compare the say a new measure that I'm developing to some gold standard to see if they're highly correlated with one another. In this case, for example, maybe I've developed a new measure of depression and I want to compare it against a gold standard like the Beck Depression Inventory. So I get a sample of participants, I give them both scales, and then I calculate a correlation between their depression score on my scale with their depression score on the gold standard. And again, a score of 0.8 or above would be considered a pretty high score and therefore would be suggestive that the new scale is measuring the same thing, that it's valid. And finally, and the way in which we're going to be using correlations is to make predictions, right? And again, kind of going back to that previous example, it asks the question, is a person standing on one trait related to their standing on a related trait or similar trait? So in this case, to what extent is high school GPA and SAT score correlated? Or we could ask, to what extent is high school GPA correlated with freshman year college GPA? One thing to keep in mind about correlation, this is the last sort of point that I want to make, is that correlation does not imply causation. So part of the problem with this is that when we conduct correlational studies, because we're measuring two traits at exactly the same time, we don't know which trait preceded the other, right? Now, we may have a theory, like if we're looking at, say, personality and drug use, we may have a theory that the person's personality developed before their drug use did. But the truth is that maybe this could happen, that using drugs changed their personality, right? So because of the fact that they're measured at the same point in time, we really can't draw any conclusions about which caused the other. So when we interpret a correlation, we say that there is an association between the two traits. We do not say that one trait causes the other. All right, so the next slides, or the next lecture is going to cover regression analysis.